My name is Yahya Foda, and I'm a PhD student in Loughborough University, supervised by Ricky Wildman and Henk Versting. So, my main presentation is about applications more than fundamentals, however, I've done some fundamental stuff in it, so I'm trying to do an experimental and simulation study of dry powder inhalers. So first of all, this is a typical flow of a dry powder inhaler while after exiting from the inhaler. So it is mainly used for drug delivery through or to lungs, as we see here. So we have the granular media going through the lungs to cure the disease, whatever. So it is mainly used for asthma, but sometimes it is used for other drug delivery, like there are some trials for using it for insulin delivery. So now about the inhaler itself. So we have this like a general dry powder inhaler surface or geometry. So we have the packed dose down here, and generally it consists of two sizes of the particles. So we have carrier particles, mainly lactose, and the drug particles as well. And the flow is mainly triggered by the patient suction. So this creates a multiphase flow and fluidize the particles, and they are removed from the inhaler. So there are several dry powder inhaler models. So this one is named Discus, and it is mainly using jet fluidization pattern. So the air is coming from here to fluidize the particles, and then the particles go outside here. And the other one is turbohaler, which uses a simple inline flow. So the physics in the physics of multiphase flow and the dry powder inhaler. So we have dense solid particles which are flowing, so they might interact with each other by friction or collisions. And also we have the air flow, which creates a multiphase flow system, and there are air particle interactions through momentum transfer drag, for instance. And also there is a point of experimental validation of this process, taking into account that the flow is dense and unsteady, and the process happens very fast, within 3 seconds. There are other challenges which I'm not concerned with in this study, so it's like cohesion and turbulence and detachment of the drug particles from the carrier one. Now, the aims and objectives of this study. So the first objective is to test the multiphase hydrodynamic models. So this is for unsteady flow, and in order to simplify the process, it is for non-cohesive powder and monodisperse as well. And the model or the geometry configuration which I'm using in this study is jet fluidization, the one which resembles the Discus model. The other objective is to have an experimental validation for this model. So we want to measure the particles' velocities and positions throughout the whole test section or the whole domain instantaneously. So we want to have at every time frame the positions and the velocities of the particles. And we decided to go to the optical technique because it suits this process. So now to the experimental rig. So we have here, this is a 2D test section. So this means that we have the depth of the test section is slightly larger than or equal to the particle's diameter, which is here 4 millimeter. And by using this type of test section, it is quite easy to detect the particles, and by applying Hopf transformation and then track them throughout the experimental time, whatever like we are using, and then construct the velocity vectors using numerical differentiation. And about the airflow inside the test section, so we have here an outlet port for the air, and a wire mesh is constructed or is mounted at this port to prevent the particles from being removed outside the domain. And we have an air inlet from here. So the whole airflow is triggered by this pneumatic suction circuit. I will describe it in detail in a minute. And then we measure the pressure, outlet pressure and inlet pressure to the test section using fast response pressure transducers, one that like mostly used in engines, so that we could get the transient or the unsteady profile for the airflow. Now these are the experimental rig components. So this is the vacuum pump driving the whole system, and this is a test section, and we can see the pressure transducers here at the inlet and at the outlet. This control unit controls the process since we are doing transient or unsteady flow, and we have an interface with LabVIEW to control the experiment. Regarding the optical rig, we have 12-volt halogen lamp used here, and it is powered by direct current so that we prevent or avoid any fluctuations in the intensity of light throughout different images. So we make sure that the optical technique works well. And also we capture the images using high-speed camera with a frame rate of 1,000 frames per second. Now the result is the experimental result. So we've done this experiments for two cases. The first case we got full fluidization as seen here. So all the particles inside the bed were removed and stacked at the top of the domain as we see here. This is after 700 milliseconds. This is the experimental time. And this is mainly due to the high pressure difference between the inlet and the outlet. So we got here 7 kilopascal vacuum at the inlet and 22 at the outlet. This slide shows the velocity vectors for different frames. So we have here, as we see, we can see strong convective flow at the early time of the experiment, and still like we have this convective flow here as well for another time. The second case, we have here lower pressure difference. So we got after 2 seconds this what we call partial fluidization. So a part of the bed is removed. Some particles are stacked at the top of the domain, and some particles are just moving around in this freeboard region. And as we see here, the pressure difference is much lower than the previous one. So we have the inlet at 3 kilopascal vacuum and the outlet at the steady state is around 5 kilopascal vacuum. And this shows the particles velocities as well. So we have here this shear fluidization, if we call it, or moving here, and we have some random motion of particles as seen in this figure. So now about the model which we're using. We are using Euler multiphase flow model. So it treats both phases as continua. So we have two sets of equations, each of them describing one of the phases. So we have a set of equations describing the air phase or the gas phase. So we have the mass equation and the momentum equation as well for both phases. And of course, this is the term which accounts for the momentum transfer, or mainly the drag. So there are some auxiliary conditions or sub-models used here. So for the kinetic theory models, we've used Poslan and Garzo and Dufty, and some slow flow models for the case of the very high packing fraction at the initial state, drag models. And also for the inlet and outlet pressure boundary conditions, they were measured from the experiments, and we feed these conditions to the model so that we can mimic what is happening exactly in the experiments. And the equations were solved using MFIX, which is an open source code, and on a uniform 2 millimeter mesh. So now, in order to have and this was the main aim of going to this 2D test section, to have quantitative results. So we decided to divide the domain into two regions. This is the freeboard region and the bed region, and then compute different variables at this region and compare the experiments with the simulations. So we have the velocities and the void fraction for both approaches. This slide shows some qualitative comparison between the particles flow, the images taken from the experiments, and the void fraction profiles. So this is at different time frames. So as we see here, like this is, we can call it as qualitative comparison because the void fraction is not the same as the particles position or the particles or the frames taken from the experiment, but we can see a nice qualitative comparison between the both approaches, and this clears that we have highly convective flow in most of the cases or throughout the run. Now this is a comparison for the freeboard void fraction for the both approaches, and we can see that we have good matching between the two approaches for the void fraction. Regarding the vertical velocity, so this is comparison between the simulations and the experiments. So we can see here that we have higher gradients for the simulations in both the increasing trend and decreasing trend compared to the experiments. We're still thinking about this point, probably because of the difference between the both approaches. And now we try to compute the granular temperature for both approaches. So this is for the model, and this is for the experiments. The point is that we have here a very narrow curve for the model compared to the experiments. Probably or most likely this is due to the way we calculated the granular temperature. So here we calculated the granular temperature based on all of this freeboard region, which probably is not the right way of doing it. We need to subdivide this region to different regions because here we have almost zero velocity here and there. So, and this, while taking into account the whole freeboard region, this might contribute to the granular temperature at different time frames here. Now this is the second case for low pressure difference. We got partial fluidization, and this is comparison. So as we see, we have also, especially at the early frames, good qualitative comparison between the two approaches, while here it is not as the same as here. Some discrepancies is happening here, so we will need to see what's going on for the curve or the quantitative comparison. So this is the comparison between the experiments and the simulations. So we have for the experiments this fluctuation in the void fraction, and we have for the simulations like a bit smooth curve here. This is the vertical velocity comparison for in the freeboard region. So as we see here, this is the simulations. So it is mostly constant at zero at this point or at this range, and this is still fluctuating for the experiments. So there are some discrepancies here also. This is probably due to, I'm thinking that this is because we have very or a bit large particles, which might causes some discrepancies in the flow while taking this into account. So the summary, we've done experiments and simulations for both cases, full bit fluidization and partial bit fluidization. And also we measure the granular temperature in one of these cases. We need to check the averaging region for computing the granular temperature, and probably obtaining the velocity distribution for the particles would help in this, and comparing this with the one assumed in the kinetic theory models. So thanks for your attention, and I'm happy to answer questions.
Yes. Well, in the graph you plot granular temperature over time. Is this an average temperature? Is it a local temperature?
No, it is instantaneous.
Instantaneous?
Yeah.
At a given point?
No, over the whole region, the freeboard region.
Average temperature?
Yeah.
it's a follow-up question on that. Charlie Campbell years ago did an experiment, I think, where he measured the granular temperature in the fluid ice bed and found that it was highly correlated with the passage of bubbles. And in general, that kind of means that the granular temperature definition is not very useful when they are large in homogeneities, because it's hard to define the base state, if you like, from which you can subtract the velocity from the mean velocity. So is there any...
Yeah, this is right. Yeah, this is right. I know it's like, because we have this especially high gradients and large particles as well, so it might be difficult to this. We're still thinking of how to do this now.
Okay, first of all, I have to say I did not measure the granular temperature in a fluidized bed. I measured the particle pressures exerted on the wall, and I don't think they're honestly related to the granular temperature. They're related to defluidization of the bed by the passing bubble. And the stresses were largely elastically distributed out to the wall. But I have sort of the same question, and that is, what did you subtract off? What was the mean velocity you subtracted off, and how could you differentiate the thermal fluctuations from turbulent, like that is ordered fluctuations between the particles?
Yeah, well, the mean velocity which was computed just was this for the whole particle.
In other words, you got one number there for the mean velocity.
No, we have for the x direction and the y direction. So
okay, you have two numbers.
yeah, and then the fluctuations for all the particles around this.
So the granular temperature then was the instantaneous particle velocity minus one of those two numbers.
Yeah, summation over all the particles.
Okay. I would suspect that that is the complete source of your discrepancy.
Last question, please. Oh, yeah, okay. Yeah, so, I mean, are these actually collisional? I mean, do you see particles bouncing off each other and stuff?
Well, for this high velocity regime, no, very few we see the collisions.
So it's mostly because of turbulent fluctuations that you get a velocity fluctuation. Is that right?
I think it is like for this case, because we have also like some fluctuations in the mean velocity, and this is taken into account while computing this. So this is why we need to make the regions much smaller.
Last question, while the next speaker please sets up.
It's only a comment. See, and since there is two relevant direction in your problem, I guess that probably there will be two relevant directional temperature in each one of the directions.
Yeah.
Relate this on something like anisotropy, or you can measure it.
All right. With that, let's thank the speaker.